Braintree is an AI company. It's a research and development AI company. So we have a research lab where we investigate some fundamental theories and we try and generate new algorithms. This includes work on modeling spiking neural networks. So we're trying to understand how the brain works better. We've got researchers looking at how cancers change over time. And so we're looking at agent-based models going down to the cellular or genetic level. Because tumors evolve and change over time. And if you apply therapies to kind of counteract the growth of a cancer at the wrong time, it'll have a detrimental effect to the outcome that you're looking for. So it's important to really understand the nature of an individual tumor with an individual patient. So we're trying to help step towards tailored cancer treatments with that work. We're looking at ensembles of neural networks for autopilot systems. So we've got an intelligent autopilot system that can fly aircraft more effectively than human pilots can, even when that aircraft is undergoing significant damage. So we can literally knock out the engines or have horrible weather conditions that a human pilot cannot cope with, and this intelligent autopilot will be able to do an emergency landing and do all the necessary procedures or keep the plane flying as though nothing's happened. We're looking at new combinations of techniques. So can we create graph-native machine learning algorithms, machine learning that's designed to work with graph-structured data? Or can we combine reinforcement learning with multi-agent techniques? As called MAL, multi-agent reinforcement learning. Can we have multi-agent models automatically fine-tune themselves? So those are some of the things we've got going on in our research lab. I'm still a professor at University College London, so all of my team are based here, as well as those that Braintree sponsor. We also have a consultancy department, and we do consultancy for large organizations who basically want us to do machine learning and data analytics for their various problems. And we have some of the world's largest retailers and manufacturers that we help with their various issues. And finally, we're looking at product development, of which we have several things that we're working on, but perhaps I won't go into those at this point. In the beginning, when we first started using evolution to solve problems in computers, we regarded evolution as something of an optimizer. Let's say it's quite an approximation of perhaps what evolution really does, but you can think of the genes in organisms as being improved, if you like, changed, optimized over time to enable living creatures to have correspondingly useful phenotypic features, in other words, traits. So one thing we've been looking at recently is agent-based modeling of people. If you can, in an evolutionary algorithm, if you can model, let's say, organisms in terms of their genetic structure and evolve their genes over time, why can't you do that in terms of understanding how people interact? So what if you have a population of people that have to collaborate to solve some kind of problem? Well, most existing models, and there are existing models that they're used throughout economics and related fields, they try and model how we might behave in different circumstances to try and understand maybe how to negotiate or how to set up businesses or how to run the economy even. What's the basis of creativity in humans? I don't think we know the answer to that. However, there are many hypotheses about what that might be, and one of them is that somehow it resembles an evolutionary process. That somehow ideas are combined and mutated and almost evolve in the minds of many of us over time, like an evolutionary process. Richard Dawkins was one of the very first to kind of talk about the concept of an idea as a gene, which of course he called a meme. In one of his books, I think was it The Extended Phenotype, or was it The Blind Watchmaker? It was one of those. Anyway, it caught on. The meme of a meme is very successful. And so whether it's true or not, well, I don't know. I think it's a way of thinking. However, it's quite possible for us to model creativity using evolutionary processes, because I guess it's close enough. Unfortunately, when you look at any organization, whether it's a class of people trying to learn together, or whether it's a company, a team trying to work together, number one, actually, particularly let's say you're a company and you've got a team trying to build a product, well, it's not a coincidence that they're cooperating. They're cooperating by design. They are collaborating. Okay, and I think this is a key difference. But not enough people actually model collaboration. People working together for a common goal. This is quite different from cooperating accidentally. You know, a criminal might choose to cooperate with the police, but their aims in life are rather different. But police collaborate with each other because their aims are the same. So number one, cooperation is actually a very fundamental part of human society, and it's important that we model it. Number two, this assumption of rational behaviour. Well, if only that were the case, because then there would never be any problems in life, would there? But unfortunately, as I'm sure we're all aware, if you working in a group of people, even if you are all trying to do the same thing, you are all cooperating to meet this common goal, there are personality clashes. There are people who they think their idea is more important somehow. There are people who have a louder voice than others or a quieter voice than others. There are people who get very nervous about new things, or there are people who love to explore different ideas. There are people who are very good at detail work and people who are hopeless at detail work and good at the big picture. So the question is then, well, given all these different kinds of brains that we've got, who should be working together to be a most effective team? Which combinations of personalities are optimal to solve any given task? And whilst psychologists are great at profiling individuals, nobody really understands how to profile groups of people working together. It's long been a goal in psychology to do this. Don't really know how to do it. But actually, it's something that we can model in a computer. So this is what we've been doing most recently. We've been doing agent-based modeling, where we can actually model the way someone thinks, so the way their brain kind of moves around in a problem space. So I'm thinking about this idea, now I've got a new idea, now I've got another new idea. I'm moving around, I'm trying different ideas. And as I do so in a team, I'm communicating with you, and you're having ideas, and your brain is moving around in this problem space. So we can model the way we think as though it were a strange optimization algorithm. I'm trying to optimize my idea of what the answer is. You're trying to do the same in your brain. We communicate as we do it. And the way I do it is dependent on my traits, my personality traits. The way you do it is dependent on your personality traits. And that way we end up with a population of individuals, each with their own little personality, each collaborating in a funny way. And we can model that in a computer, and you end up with an ensemble of optimization algorithms all trying to solve the problem together. Some of them are very bad at it, some are very good at it. And through this way, and through obviously calibrating to real-world data and with the help of some psychologists as well, we're able to do really quite interesting work on understanding which groups of people should be working together. And of course, this has a lot of implications for recruitment, for managing people, for helping to train people. So we think it's quite a good thing to do. Did it? how did the onset of the Internet of Things, do you mean Internet in general or Internet of Things?
Both.
Affect evolutionary computing? I actually wish it affected it more. And maybe there's still a time for it to affect it more. In a related field such as neural networks, something called deep learning, which everybody seems to know about now. Deep learning is a really good rebranding of neural networks that my old pal Jeff Hinton came up with. So that was very successful, and the reason why it's very successful is that the internet and, let's say, cloud-based computing enables a vast amount of data to be accessible and enables a large amount of processing to be accessible. And plus a few good tweaks of the algorithms themselves. And the combination of those things result in a very powerful kind of machine learning. So that's deep learning neural networks. I personally think it would be great if the same thing could happen with evolutionary computing. I think right now evolutionary computing is not as fashionable as deep learning, as these other machine learning methods. The idea of optimization in general has slightly fallen out of favour compared to machine learning, even though the two are arguably much the same kind of thing, and you can use one to do the other. One could argue that the same large amount of data and the same access to large amount of computing power has the potential to transform the field of evolutionary computing as well. And I'd say in other fields too. I'm a fan of agent-based computing, which is related to evolutionary computing. It's another way of modelling individuals that interact, which is kind of what happens in evolution. I would argue, the future may be coming soon, that these other algorithms, evolutionary computing and its flavours, there's developmental methods, there's artificial immune systems, there's even swarming-based algorithms. All of these might benefit in time from this readily available large computing resource that we now have. But I have to say fashions come and go, and we are in a machine learning and AI fashion at the moment. You can get a lot of useful things out of biology and other disciplines, chemistry, physics. I've worked with more biologists than I remember now. Harvesting the natural world, maybe that sounds nasty, being inspired by the natural world is a very fruitful thing. And also, actually, every time we think we've invented something cool, we have a deeper look in biology, and we find that it's been there for millions of years already in some form in biology. So all these ideas that we've got in computer programming of subroutines and loops and conditional statements, they're all in our DNA. Putting myself, I'm not agreeable though, and Lara. So these three are likely to be quite agreeable, and if we're going to make it uncertain, simulate